name is Kayla and I'm an undergraduate student at Cal Poly Pomona. And in this video, I will be explaining our fifth project from the Microcontrollers Lab 3300L. I took this class in fall of 2023 with Professor Pinai. First, I will explain the purpose of this lab. Then I'll go over the wiring schematic. Then I will explain the code for the program. And finally, I will demonstrate the correct operation of this lab. This circuit uses an LMT84 temperature sensor to measure ambient temperature, and RGB LED visualizes the color temperature that is being measured by the sensor. I also use a photoresistor to create night or day conditions for different output results. This lab is crucial for doing well in the remainder of the class because the final circuit is the creation of a remote-controlled thermostat with a smart heater and an alarm clock. The code required from this lab is used henceforth, so a solid understanding of the material is required. The purpose of this lab is to cover the basics of converting analog signals to digital data that can be displayed and verified on the circuit. The Intro to Microcontrollers class uses the PIC18F4620 microcontroller. It is programmed with the PIC4 and MPLAB IDE. My microcontroller is mounted into a prefabricated development board that is designed by Pinai. So I will be skipping over some of the header pieces shown on the schematic. Pins 32 and 11 are getting 5 volts DC input directly. Pin 5, I have 5 volts applied to this 33 ohm resistor. The LM4040 is a voltage regulator, and high voltages will sink to the ground so not to damage the development board. The jumper wire must be across pins 1 and 2 on header 3. The output of pin 2 from header 3 goes to pin 5 of the microcontroller. Pins 31 and 12 of the microcontroller feed to ground. The first RGB LED, D1, is an output of port C and uses microcontroller pins 15, 16, and 17. The second RGB LED, D2, is an output of port E and uses microcontroller pins 8, 9, and 10. The third RGB LED, D3, is an output of port C and uses microcontroller pins 18 and 23. On the third LED, the assignment does not ask for any red color mixing, so that stays open, while we only use the green and blue LED assignments. Pin 2 of the temperature sensor is an input for port A and terminates to pin 2 of the microcontroller. Pin 1 of the temperature sensor receives 4 volts DC, and pin 3 goes to ground. The photoresistor inputs to port A, pin 4 of the microcontroller. Pin 5 of the microcontroller is used to compare reference voltages. Port B outputs to the tens place 7-segment display using microcontroller pins 33 through 39. Port D outputs to the ones place 7-segment display using microcontroller pins 19, 20, 21, 22, 27, 28, and 29. This particular program is all written in C. I like C more than assembly because it feels more intuitive and efficient than assembly. These are the standard header files I use for pretty much every microcontroller lab. stdio.h is the standard input and output header files for C language. stdlib.h is required for accessing general purpose C functions. xc.h allows the source code to access the features of the PIC18F4620. Math.h allows us to do various logic and mathematical subroutines in my source code. P18F4620.h is necessary because this will allow the MPLAB compiler to address the registers of the PIC18 microcontroller appropriately. This is essential for timing, interrupts, and bit control, such as flags, enables, and priorities. MPLAB will also not be able to debug and program the PIC18 without this header file. USART.h is the header file for serial communications. USART is short for Universal Synchronous Asynchronous Receiver Transmitter. For this project, this header file is necessary for observing the output of print statements from the source code. I use TeraTerm to read the output of these print statements, and this is very useful for debugging code when I encounter issues. And also it confirms that the voltage readings are being calculated correctly within the microcontroller. After the header files, I have this section I call global declarations. Int IO67 is describing an internal oscillator for clock timing. The watchdog timer is initially turned off. If it was originally initialized to on, then when the microcontroller is programmed, the watchdog timer would not allow the code to load and run properly. LVP is the single supply ICSP. ICSP means in-circuit serial programmer. This allows for the microcontroller to be programmed while built into its final circuit design. For this lab, that is not needed because the microcontroller is already built onto a test board with a dedicated header for the programmer to be attached. BOREN is set to off. This is the brown out reset enable bit. This is so that while the microcontroller is being loaded, brownouts won't turn off of the microcontroller and interrupt the loading of the program onto it. The remaining global declarations are the assignments of the red, blue, and green legs of the 3 color mixing RGB LEDs. The legs are physically wired to each of these ports, and this definition offers a way to easily name them for writing the subroutines in this code. D1 stands for diode 1, D2 is diode 2, and D3 is diode 3. Now that the header files and configuration bits are set, I get into defining the 7-segment display. The display I used is common anode. This is important when figuring out how to display the numbers, because a bit value of 0 will turn on the LED of that segment. I drew a truth table to help identify what the hex values I would need to have to output onto the display correctly. The most significant bit is always 0. After I identify which segments are lit for each number, going from 0 through 9, then I convert this value to hexadecimal and write it into an array length of 10. Next part of the source file is the writing of the subroutines that I will call upon in the main function. First is the delay function. This is a for loop, and the 17,000 comes from the internal clock of the microcontroller, which has a frequency of 1 MHz. This function delays 0.017 seconds and slows down the refresh rate of the LEDs so that they are visible to the human eye. The initialize UART function lets the transmission and receiver interrupts to be off. The USART is asynchronous, the data is 8 bits, the USART continuously receives data, and the high baud rate is set. OSC-CON means that the clock of the microcontroller is set to 1 MHz. I get this hex value from the datasheet of the PIC18. Put is a function used by teraterm. This is a serial transmission function that takes a char C and will shift through the chars of a print statement and output them to teraterm. This function here is used to initialize the analog to digital converter. Analog digital control register 0 only implements bits 0 through 5. Bits 7 and 6 are always going to be 0. Per the wiring diagram, the LMT84 temperature sensor is connected to RA0. This means that bits 5 through 2 are all zeros. Bit 1 is set to 0, so the AD conversion is idling until instructed to begin from the source code. Lastly, enable the AD converter by letting bit 0 be 1. This is a hex value of 1 that you see here in the function. ADCON1 is the analog digital control register that configures what ports are analog or digital. I continue to rely on the datasheet and notice bits 7 and 6 are unimplemented. Bit 5 and 4 are 0 and 1, meaning that the reference voltages are VSS for the return voltage and VREF positive for the positive voltage. Bits 3 through 0 indicate which pins are analog or digital. AN2, AN1, and AN0 are receiving analog signals from the temperature sensor and the photoresistor. The rest of the pins are digital or unused. Therefore, the binary value 00011 converted to hexadecimal is 1B. ADCON2 is the analog digital control register that influences the clock timing of the system. Bit 7 is 1 to indicate a write justified format, meaning the system is a 10-bit operation. Bit 6 is always 0. Bits 5 through 3 are the acquisition time select bits. They are used to control the sampling time of the system. This is set to 12 cycles. Bits 2 through 0 are the conversion clock select bits. 001 selects 1 megahertz over 8. Therefore, 12 TAD times 8 microseconds is 96 microseconds, and that's what's used to measure the analog voltage signal. In hexadecimal, this is a value of A9. This is a function that reads the incoming voltage of the temperature sensor. Each analog input pin is multiplied by 4 in order to stay consistent with how each analog channel is 4 bits and a positive offset of 1 is included so that the correct channel is aligned with its corresponding pin number. This next function is used to output the lower 4 bits to port D and onto the 7-segment display using the array created above. The next function outputs the upper 4 bits to port B's 7-segment display. This function will read the analog voltage values from the temperature sensor by first starting the analog to digital conversion, then a while loop that continues until the flag for completion is triggered. This will store the result of the temperature reading as an 8-bit value. This set of functions are used to define the color mixing of each color of the RGB LEDs. I repeat this for all 3 LEDs. It gets a little bit redundant, so I'm going to scroll past this. Finally, we have made it to the main function body. The first things that we need to do are called the initialize UART function and the initialize analog to digital conversion function. Then, I want to initialize all of our utilized ports according to the wiring schematic. Port A is an input, and ports B, C, D, and E are outputs. Now that our clocks are running and analog signals are converted to digital, the next thing for our program is to pass those converted values to the 7-segment displays. This while loop is always true, so it will not break until the termination of the program run. Then I call the set ADCON0 function. Then I need to convert the measured voltage values from the temperature sensor to millivolts, and then to degrees Fahrenheit. Numstep is the variable that holds the digital value before conversion, and then I multiply by 4 to get it into millivolts. Next, I use a given formula from the lab manual to convert to degrees Celsius. Lastly, I can convert Celsius to Fahrenheit using the relationship degrees Celsius times 1.8 plus 32. The 7-segment displays can only show integers, so the converted value must be converted to an integer and then shown on the displays. I want to check that the 7-segment displays are confirmed by the actual measurements from the PIC-18, in case there are any issues that need to be debugged. So I output to the tare term with some print statements. These automatically are communicated using the push function from earlier. Lastly, the lab manual asks for visual indication from the RGB LEDs. If the temperature is less than 10 degrees, LED 2 is off. If the temperature is greater than 70 degrees, LED is white. If the temperature reading is less than 40 degrees Fahrenheit, then LED 1 is off. Between 40 and 49, it is red. Between 50 and 59, it is green. Between 60 and 69, it is yellow. Between 70 and 71, it is blue. Between 72 and 73, it is cyan. And greater than 73 degrees, it is white. LED 3 is a visual indicator of the photoresistor's values. If it is not receiving light, it is off. If the light received measures between 2.6 volts and 3 volts, it is blue. If it measures between 3 volts and 3.3 volts, it is cyan, and if it is receiving full light, it is showing green. So, as you can see, the reading of our analog values from both the temperature sensor and the photoresistor are correctly converted to digital signals and are outputting as directed.